Hello AP Statistics students. In this video, we're going to take a look at the four-step process it takes to make a confidence interval, okay? There's a lot of context involved. There's a lot of check boxes that have to be checked to make sure you are making a confidence interval under the right conditions, correctly, and with the correct interpretation. So that, like I said, there's a four-step process here. We're not going to do the whole four-step process. Here's the gist of it. We have to state what we're going to do, make a plan, then we actually have to do the confidence interval, that's the math, and then we have to conclude, make a conclusion for what the confidence interval means. In this video, we're just going to focus on the first two steps, which are, yes, the most boring ones, but they are sort of necessary because they set everything up, kind of important, the setup. So we're going to do the state and the plan of those. We've actually sort of done the conclusion already. You know how to interpret a confidence interval. You've written that sentence. So that means next time in class, we simply have to do the do. Want some Mountain Dew? So, state is the first part. Communication is important. All right, that is why we start with the state. No, not like the state of California. State is meaning saying a statement. We must state what we are doing and what we are estimating with our confidence interval. This is mostly just context. Okay, we're saying the context of what we will be doing. Then the next part, plan. All right, we must declare what procedure we're going to be doing and, more importantly, why we're allowed to do that procedure. Okay, there's conditions that have to be met in order for you to do this procedure. Yes, these are those conditions that we've started doing a little bit with the normal condition and the 10% condition. Those are included in this. Those are the reasons why the math works. And so every time we do this procedure, we have to state why we know the math works. It's just good procedure, good practices to be clear in our math. So let's do a quick example of this so you can see it. Hopefully you realize it's not that bad. And it will clarify what it means to state what you're doing and then plan what you're doing. So, a recent poll of 738 randomly selected cell phone users found that 170 of the respondents admitted to walking into something or someone while talking on their cell phone. Psh, I've never done it. Construct and interpret a 95% confidence interval for the proportion of all cell phone users who would admit, there you go, who would admit to walking into something or someone while talking on their cell phone. All right, so first we got to state what it is that we are doing. So we are going to make a 95% confidence interval for P. All right, now, you do need to then say what P is. P is the true proportion. Wow, I cannot spell proportion. There we go. What a save! All right, the true proportion of cell phone users who would admit to walking into someone or something while talking on their cell phone. All right, so we just stated what we're going to do. Again, that is mostly context, isn't it? So, plan. What's our plan to get this confidence interval? Well, we are going to do a one sample Z interval. That's the technical name for a proportion. Wow, I cannot spell that word. That's the technical name for this confidence interval. A one sample Z interval for a proportion. Or you could say for P. We sort of have defined P already. So you can sometimes just say for P. That's the technical name of what we are doing. One sample, yes, we will do two samples eventually. Z, because we're going to be using Z star to do our confidence interval. We talked about that a little bit, but we'll talk about that more in our calculations tomorrow for this proportion. Now, why are we allowed to do this one sample Z interval? All right, here's where we have to check what's called the assumptions and conditions. All right, the first one is the random condition. All right, we have to be taking a random sample. So look at the problem. Are we taking a random sample? A recent poll of 738 randomly selected cell phone users. So yes, this comes from a random sample of 738 cell phone users. It has to be from a random sample. Sometimes you'll even see in the book, or you'll probably see me do it, we'll then just put a big check mark for the random condition. Yep, we got the random condition. If we want to take our conclusion and apply it to the whole population, we have to randomly sample from that population. All right, that's why this has to be random if we're going to apply what we learned to the entire population. The next is our good old 10% condition. All right, we have to be sampling less than 10% of the population. Now, in this case, I guess it's technically an assumption, but it is safe to assume that that our sample of 738 is less than 10% of the entire cell phone using population. Perfectly reasonable to make that assumption, but we do need to tip our hat to that to say that yes, we are sampling less than 10% of the population. That, of course, is so our standard deviation equation works, so that we can sort of ignore the fact that we're sampling without replacement, which messes up independence. But because we're doing less than 10% of the population, we can sort of ignore that issue, okay? But again, that's just one of the conditions we have to make. All right, and last, the large counts condition. All of this is based off the normal model, right? We need our sampling distribution for these samples to be normal. That's how our 95% confidence interval is based off, or any percent under the normal curve. So how do we know our sampling distribution would be normal? If we have more than 10 successes, more than 10 failures, okay? So we have to check n times p and n times q. So we come up here, we see that we have 170 of the respondents admitted to walking into something or someone. Now here we can actually sort of shorten this. I need at least 10 successes and 10 failures. Well, I know there's 170 successes. So I don't necessarily have to do n times p. I don't have to go to the proportion. I have the actual count. So I have 170 successes. And that means I have 738 minus 170, which is 730, yeah, which is definitely bigger than 10, right? So 738 minus 170, which is 568. which are both greater than 10. I might say greater than or equal to be very precise. So our large count condition has been met. Put a check mark next to that one. That means our sampling distribution will be normal, which means we are allowed to continue on with our confidence interval. We would then calculate it. Again, we're not going to do that this time. I'm going to keep this video as short as possible. That's going to be next time when we actually calculate it. But once we got our interval, we would then write our conclusion. So I'm hoping this sentence sounds familiar. We are 95% confident that the interval from 0.20 to 0.26 captures P, which is the true proportion of all cell phone users who would admit to walking into something or someone while talking on their cell phone. Now, of course, we don't know where this interval comes from yet. We don't know how to calculate this yet, but that will be our next plan. This is the do stage where you actually do the confidence interval. So we'll learn how to calculate that next time, but I'm hoping that sentence again sounds familiar. So real quick, I want to go over those assumptions and conditions again. Okay, what are they and why do we have them? First, the random condition. Our sample must be random if we want to apply what we learned to the entire population. All right, you have to randomly sample from your population of interest. Okay, we've learned that a long time ago, but it's worth stating again, and we have to continue to state and check this condition. The 10% condition. So our standard deviation formula only works if our observations are independent of each other. Okay? But sadly, this is technically rarely the case. All right? Because we sample without replacement. All right? If I do my random sample of cell phone users and I pick George, I don't put George back in the hat to where he could possibly be picked again. That technically changes the probability that the next of how likely it is the next person is chosen or who's chosen, because the total population changes when I pull George out. Okay, that changes the total population. That changes your probability. It changes the number you're dividing by. Our standard deviation formula doesn't really work that way. But if we're sampling less than 10% of the population, that issue is really very, very small. Okay? If I have a total population of 1 million, and then I take one person out, now the population is 999,999. It didn't change enough for it to make a difference. And that difference stays small enough if you sample less than 10% of the population. Okay? So we can ignore this issue. Oops. Man, spelling is not my strong suit this morning. We can ignore this issue if we sample less than 10% of the population. So that means we get to use our standard deviation formula. And the large counts condition, this is all based off a normal sampling distribution. All right, that's why we studied chapter 7 before this, sampling distributions. This only works if that sampling distribution is normal. And that requires a large enough sample size. Now remember, there's two ways the sample size can be large enough. All right, if you have proportions, that means successes and failures are greater than or equal to 10, right? But for means, that was simply the sample size is greater than 30. So we did the proportion ones, but it could also be if you're doing a mean, an average, then the sample size has to be bigger than 30. Once that large counts condition is met, boom, our sampling distribution is normal, and we can do this math. So every time we do one of these, we do have to sort of check box those 3 conditions, okay? These are the conditions for inference, all right? Everything we're doing right now this semester is statistical inference. What the heck does inference mean? Inference, a conclusion reached on the basis of evidence and reasoning. Okay? Well, we're trying to make a confidence interval. That is our conclusion about a population. Our evidence and reasoning are the sample we take, because you can't actually know a population proportion. You can only take a sample and use that as evidence to make a conclusion about your population. All right, that's why this is called inferential statistics. We are making an inference based off a sample. All right, I'm hoping that 4-step procedure makes some sense. Remember, we only did the first 2, the plan, or the state and the plan. We state what we're going to do. That is basically just context, right? We make a plan. We state the specific name for what we're doing, the 1 sample z interval for a proportion. We check our conditions. We calculate, which we'll do next time, and then we write our conclusion. All right, I hope that makes sense to everybody.